Okay, so good evening. I'm going to talk about Professor Pierre Francus, introduce him. It's a great pleasure to have him here at the University of São Paulo give this talk on Varves, scanners, and paleoclimate. Professor Pierre Francus, he is a professor at Institut National de la Recherche Scientifique. Sorry for my bad French pronunciation, but he works for an institution in Quebec, Canada, which is an institution that has French as a first language. And talking about a little bit about Professor Pierre Francus, he is from Belgium, and he got his master degrees and PhD degrees and bachelor's degrees in Louvain, which is the University of Catholic of the Louvain, in Louvain, Belgium. It's a very famous institute in Belgium. And he did his bachelor's in physical geography, and his PhD is in geosciences, and more specifically in lake sediments, and also geomorphology, physical geography. And for his postdoc, he did his postdoc at University of Massachusetts, MRS, so you overlapped a little bit there. That was in 2003, 15 years ago. And it's a pleasure to have Professor Francus here since you haven't met for many years. And also it's interesting to have him talking about specific things about some lake limnology and XRF scanners and things about how to use these sediments of Varves as a proxy for paleoclimate. Specifically, he'll be talking about lakes in Arctic. I know that he goes to many lakes and everywhere in many places, but he's more into the Arctic lakes. Okay, Professor Pierre.
Thank you very much for this introduction. It is also a pleasure for me to be here for the first time visiting Brazil, and very glad to meet again with Professor Francisco da Cruz. And so without any other interruption, I will start the presentation. You read the title already, and you said the title, so I don't have to go back on that. I will just introduce you to the outline, what I'm going to talk about. First of all, what is a Varve? What is the definition? And I will briefly go over the different kind of Varves that you can see. All these pictures here are pictures of Varves that are very different. Where we can find these Varves, and so that will be one part of the talk. Then I will outline 4 different kind of scanners that allow to do high resolution analysis of these Varves. And of course, I will explain why this is interesting for paleoclimate studies. So the definition of Varve, this is a word that has been that is Swedish in origin, that was defined already in the previous in the 19th century, and it was meant to designate rhythmically deposited proglacial clays. So the proglacial clays that were deposited when the big ice caps in Scandinavia and North America retreated after the last glacial maximum. Now, it also includes all the annually deposited laminae in lacustrine and marine settings. And here you can see a photograph. This is visible in outcrops all over the places in New England and in northern Scandinavia. So 4 types of Varves, very quickly on definitions. The first one that you will see many examples in this presentation are clastic Varves. They are typical for cold environments and of course the Arctic. And basically, we have a layer that is deposited during summer when the snow melts. And there is often a graded bedding with the coarsest material deposited at the maximum peak of the discharge. And in winter, we have what we call a clay cap. These are mainly the sediments that are deposited under the ice during winter time. Here you have an example, a real picture of a real Varve. This is a picture of a sediment core. Here, this is a thin section and the picture is taken in cross-polarized light, so you can see the thickness of these Varves are quite variable. And on the right side here in black and white, this is a picture of this Varve that you see here, taken at the scanning electron microscope in backscatter mode, where we can really see here the graded bed. So you have the coarse silt that are these light points that are fining up, and here you have what we call the clay cap. So the idea to use these classic Varve environmental proxies is that basically you have here the Varve that are formed, and here you have the hydrogram that you can have during different seasons. And basically, when you have high discharge, you deposit a thick Varve, like here 1 and 2. And if you have if you have not a lot of hydrological input, you have a thinner Varve. So that's the idea of using this as a paleoclimate indicator. Second type of Varves, these are the biogenic Varves. They are typically found in temperate climates and in productive lakes, and they are mainly composed of organic matter and a layer of diatom. Usually the diatom sometimes is 2 layers, one during the turnover in spring and another one during the turnover in autumn. And often, because you have variation in the water column, especially in the oxidoreduction condition in the water column, you have precipitation of orogenic material. So there is a lot more variability with these biogenic Varves, but basically this is a model that is very general. Here I show again a picture of biogenic Varves. This is a picture of the sediment core. And on the right side here, that's a picture at the petrographic microscope. And if we go, basically in this site, this is Lake Suigetsu in Japan. We have one layer that is rich in diatom and another one that is due to orogenic precipitation of siderite, which is iron carbonate. It's basically better seen in polarized light, where you see the light points here are the minerals, the siderite that are visible at the petrographic microscope. The two last kind of Varves, these are the endogenic and endogenic Varves, and then most of the Varves, biogenic, clastic, are usually taking a little bit of the different elements. So you rarely have pure plastic Varve, pure biogenic Varve, and pure endogenic Varves. So here the core is coming from from Chad, and you see the sediment core here. You have here a picture, a close-up of one part of the surface of the core. Here, a petrographic microscope view of the Varve. And on the right side, again, a scanning electron microscope image in backscatter mode. And you see here a layer of very dense micritic calcite minerals that are precipitating in the water column due to supersaturation of the lake water. And you can see here the elemental maps that we can do at the scanning electron microscope. You can see here this is calcite in green. And you see there is another layer that is in red here, silica. If you look back to this bigger image, you see these are silica grain that are rounded. It's basically sand that is winds blown within the lake during the windy season. So we have here the alternance of a windy season and super saturation that produce the migrate. So where we can find these varves, it's basically almost everywhere. You see a map here of the known varves, of the different known varves, but these are the exception. Compared to the number of lakes, there are not that many varve lakes. You have to look for them to find them. It's really difficult to find them. So what are the conditions to have varves? You need to have a seasonal contrast. So in the Arctic, that's easy because you have ice cover and then you have no ice in the landscape. But in temperate region, you need also to have seasonality in the lake where the processes within the lake have a strong difference between the seasons. You also need to have a sediment flux that is high enough, in a sense that you need to see the varves, and so you need to have enough input of sedimentation to be able to form them. So it's usually highly productive or a lot of sedimentary discharge that brings material from the watersheds. And so you need to form these varves, and you also need to preserve them. So you need to be away from bioturbation, and this is usually the case in deep lakes or anoxic lakes, at least lakes that have an anoxia at the bottom. So to give you an idea, in the existing database, we are only 64 varve chronologies that have been reported. There are more varve records, but they are not all reported and stored in the database. In the coastal marine settings, we have also varves. Well, in the marine settings, we find varves only on the coastal margins, where sedimentation is high enough. You will never find a varve into the deep sea because you don't have enough sedimentary flux. So that was the first part with the different types of varves that we can find, and I will now walk you through the different scanners that have these are very nice tools because they are basically non-destructive. So you scan your sediment cores, and you can still have the entire material for other analysis. So the first one is the medical CT scanner. Basically, it works like this. You have X-ray source that turns around the sample that it will be here in the middle of the gantry, and the detector are just turning at the opposite side of the X-ray tube. So the X-ray are attenuated by the object thickness, the density of its material, its effective atomic number, and the porosity. So each material is characterized by an attenuation coefficient that is mu, and in the medical CT scanner, these attenuation are normalized with the attenuation of water. So if you use medical CT scanner, you will have values of attenuation that are expressed as Hounsfield units, which is the scientist who developed this technique and got actually a Nobel Prize for that. So you can do two different kind of images. So the first one is here, the topograms, and basically this is really similar to a regular radiograph, and you see here two views of one sediment core. It's very quick to be obtained. 15 seconds, you have some sort of radiograph. But you can see here the lamination in the picture. They are a little bit blurred, which is normal as in a regular radiograph. And the second kind of image that you can obtain is the tomograms. These tomograms actually is a mathematical reconstruction of all the different images that have been taken around the sample. And this mathematical reconstruction are far from perfect, especially for sediment cores, because everything in the medical world has been made for human body, and the difference between a sediment core and human body is a big difference in density. To give you an idea, the voxel size, so the 3D pixel, we'd say, have for the best scanners are 400 by 100 by 100 microns, and you can have different energies. I mentioned this because it will be a comparison with another kind of scanner. And as you can see, the lamination that you can measure or to image here are sharper compared to the topograms. This is exactly the same core. On the left side, you have the topograms that are basically blurred, and on the right side, you have tomograms that are much, much sharper. What you can do with these kind of images, when you have Varves sediments, you can measure along the sediment core, you can measure variation in the HU value, so the grade level values. And there are many tools out there that are capable to recognize the peak and the troughs and to count them and to measure them. Here an example on the sediment core from Antarctica in a marine setting. If you are interested, I can give you the exact reference later on. The second kind of scanner, these are the micro-XRF scanners. There are basically two scanners on the market. This is the iTrax core scanner, this is a Swedish one, and the Avatec, which is a Dutch one. They are working more or less the same way. There is also a Japanese company that makes some micro XRF scanners, but they are not selling a lot of them. I don't know why. So the micro XRF scanner, basically what you put your core in the left side of the machine, and basically the core is pushed under the central place, and here it's the schematics of what's happening. You have an X-ray tube that bombards the sediment core here, and with that you can have a radiograph similar to what we have in the CT scanner, and then here you have an XRF detector. And for each incremental step that you analyze, you obtain what we call an energy dispersive spectrum. You have here an example, and in this spectrum you have peaks, very high peaks of calcium, zirconium, strontium. You have here a peak of silica that is very tiny, but it's not because this peak is tiny that you don't have a lot of silica. It's just that some elements are more sensitive or are better measured by this technology than others. So there is some calibration to be done in terms of the real amount that you retrieve with this kind of technique. What is specific to the iTrax is that we have a flat beam of X-ray that can be 100 micron thick or 200 micron thick, and the effective measurement zone is 100 micron by 4 millimeters. So an example of what we can do with this scanner, you already seen a picture of these sediments, but I just want to show you. This is a very special site. This is in the middle of the Sahara, so no, Chico, I am not working only in the Arctic. So these lakes are fed by giant aquifer. That's the reason why there is still water in them. So this is the entire record. This is more than 7.5 meters, and you have two kinds of fishes. The limit is here. And I will show here the limit. So the limit between one and the other fishes. If you the plots here on the right, this is the measurement of calcium along this composite sequence. So you can see there is a big jump here. This is the measure of carbonates with discrete sample just simply by loss of ignition. And this is the ratio calcium to titanium. We often use this ratio with micro XRF because then we don't have to make a calibration in milligram per gram or something like that. And it's very handy. What is more important also is that with the calcium to titanium ratio, you basically take only the portion that is endogenic. So you remove the signal from the titanium, which is usually the detritic part of the signal. So if you zoom in, so you could think this is noise, but this is not noise. So if we zoom in on that portion, this is the thin section. These are the blocks that have been used to make the thin section. And you see all these peaks of calcium and calcium to titanium, they are really picking all the different laminations. So we can really have an annual signal by measuring these Varves with these micro XRF scanners. There are also tools that help us to measure these scanners. This is developed by the team of the Lake Suigetsu record, where you take the spectra measured by the eye tracks, you superpose them on the radiograph, and basically you can really see where the peaks are, and you can note them. And with this notation, you can really pinpoint each Varve and also the quality of the Varve. And this is a very robust way of measuring the different position of the Varves. The next scanner I'm going to talk about are the hyperspectral scanners. So basically, it works exactly the same way than the eye tracks I was talking about before. Basically, you have a sediment core here that is pushed under a camera. This is a very special camera, hyperspectral. What it means, let's say by comparison, if you have a black and white camera, you have only one channel that measure gray level values between 0 and 255. If you have a color image, you basically have 3 layers, red, green, and blue. With the hyperspectral scanners, you basically measure all the visible spectra with an interval that is the spectral resolution. Here you have one measurement, one layer for every 3 nanometers in the spectrum of the light. So basically, this is producing very, very large files. So what do you have? So for each pixel, you have a curve like this with the wavelength here. And here, that's a reflectance of that wavelength. So for each pixel, you have a curve, and you have many, many curves. And I will take the example of this red one here. What the first thing you do is you remove the background, and then you have a curve like this one below, and you see that you have region in the spectrum that are attenuated, and this is basically linked to the presence of some organic matter in the sediment. So what the people have done, so that you have here two troughs. There is one that is basically linked to the content of total chlorophyll. So you have here the depth of a trough in this scale, and on the other side you have measurements of total chlorophyll made by HPLC. And with that, you can build up a transfer function or a calibration curve to link the value of the trough that are measured in the spectrum in the hyperspectral with the hyperspectral camera. There is a second trough that is visible. Actually, sorry, I made a mistake. The first trough is the chlorophyll, the second one is the bacteriophytin. You probably don't know what it is, but it's a byproduct of some bacteria that are living at the chemocline in the lake, when the lake is anoxic. So basically, we can use the remnants, the rest of this bacteriophytin, to prove the existence in the sediment, the existence of an anoxic boundary, an anoxic line in the water column. So you said for each pixel of the image we take from the core, you can plot here the value. So you have the picture of the core, and you can plot the value of the total chlorophyll reconstructed, and on the right side you have the plot of the bacteriophytin, and you can see that we can really see where the total chlorophyll is recorded in the Varves. So even within the season, you can tell this is chlorophyll that is deposited during this season in the Varves record. And of course, you can do profiles, and these are the profiles, and you can plot that for the entire record. The last scanner I'm going to talk about is the MicroCT scanners, and this is a little bit different compared to the medical CT scanner. Here, the sample is laid vertical, and it's the sample that is rotating. It's not the source and the detector. The source and the detector are fixed. And with this setting, you can go from 30 to 230 kV, which means that you have more power to go through denser material. And depending the settings, you can have the size of the voxels. They are cubic. They are not like rectangle like for the medical CT. They are really cubic. And for very small samples, you can go down with 3 microns with this model to 80 microns, for instance. For a regular sediment core, the maximum resolution you can get, a sediment core that is 8 centimeter to 10 centimeter in diameter, you can get 15 micron resolution. So basically, the idea with the MicroCT scanner is to scan at low resolution the sediment core like here, and then zoom into a region of interest where you can even zoom in to make some reconstruction of sedimentary fabric in 3D. And here, from that thing, you can do some porosity reconstruction, even reconstruct the network. This is something that is of interest, for instance, for carbon sequestration or for geothermal energy characterization, potential characterization. So why we do this kind of zoom in is because this is taking 10 minutes to scan the core with a voxel size that is 18 microns of side. It takes 2 hours and a half if you go down to 40 microns, and it takes 2 hours and a half for a very, very small region of interest if you want to go down to the 10 micron resolution. So it's impossible to scan the whole core at the maximum resolution. That's the take-home message. And you will also get files that are way too big to be handled even with very, very powerful computers. So that is an example of what can be done. You can have very nice image of 3D direction to see, let's say, for instance, if you have a sedimentary hiatus, if you have traces of erosion or these kind of things. We have a project where we are looking to what we call the ice-crafted debris. So basically the coarser grains that are deposited on the ice during wintertime, and then when the ice melts, then you have these grains that are dropped literally into the mud. Here's just to give you an example. This is a scan that is made in a laminated sediment with an 80 micron resolution and go here to 20 micron resolution, you can see really the difference between the two, where you can really distinguish here the limits, the boundary of the laminations. And here another exercise made by our colleagues from the UK. You have a thin section and the MicroCT image just nearby with a resolution of 21 microns. So basically, a resolution of 20 microns is equivalent to a picture taken at the petrographic microscope. Because remember, the thin section have a thickness of in between 20 to 30 microns. So you cannot really have a better resolution with the petrographic microscope. Mm-hmm. The big advantage of the MicroCT scanner is that you don't have to make the thin section. And the thin section, sometimes if you look at this example in the lower left part, this is thin section. You have a part of the sediment that have been destroyed by the making of the thin section, and this is pristine in this with the MicroCT scanner. So now I'm going to show a couple of examples for paleoclimate. Of course, I will show you images of the Arctic because Chico asked me Arctic. It's a big change for people living in Brazil. So I will show you images from Cape Bounty and from Sawtooth Lake. Here we have Greenland, and this is Ellesmere Island, which is the northernmost island of Canada. And this is for this map. And then I will show other records later on that are not on this map. So this is Cape Bounty. This is Cape Bounty around mid-May. You see, weather is terrible. You will not survive. A normal Brazilian person will not survive in that environment. And this is a little bit later in the season. It can be nice times to times. You know, it's still ice covered, but at the end of August, usually the ice is melted away. But in July, you still have ice that is still thick enough to be able to land an aircraft on. So basically, here you have ice that is 2.5 meters thick. So the Varves, these are the clastic Varves. The Varves at Cape Bounty are plastic Varves, and here on the left side you have an image of the Varves, very similar to the one I showed you already before. And on the right side here you have the profiles measured with the MicroXRF scanner. You have the profile of silica, profile of potassium and titanium. And if I look at the maximum in the silica and the titanium, which are indicative of the tetrahedral input, you can see that the silica and the titanium are always linked to the coast layer. And here you can even see, this is a thicker Varve, you can see that we can see the graded bedding here, where potassium is inverse to silica and titanium. So the potassium is usually more rich in the clay, so fine sediment is rich in potassium. Let's go for the clay cap. If we look at the maximum of potassium, and here we have made the ratio of potassium to titanium to really pinpoint and recognize the clay caps, and this is really doable. And these peaks here are really useful to recognize and count the clay caps. So with that, we can have our Varve counting and the chronology established with the help of this. Of course, we will also use the peak counter software that I showed earlier. Now, what is the most difficult thing to do in the Arctic is to make correlation of what we find in the sediment and the instrumental climatic record. So here at Cape Bounty, the closest weather station is something like 180 kilometers away, and it's also very short. So we have data only for 27 years. from 1973 to 1999. And so basically what you look at is different temperature indices or precipitation indices or rainfall or snowfall, and you try to correlate the value of the zirconium to potassium ratio measured with the eye tracks for year 1999, then 1998, and so forth. And you come up still with interesting correlations, at least in earth science. This is something that is quite good. And so here what you have is the temperature for the strongest correlation are the temperature for May, June, July, August. And then we also have a good correlation with the amount of snowfall during the previous winter. And we also have an interesting correlation. So we can do that we can then plot our zirconium to potassium ratio on a calendar scale. So here we have 1,000 years. And you can see really that the last 150 years, we have an increase in summer temperature and also an increase in winter snow. And you can see here, basically, it was colder. That's probably what we call the Little Ice Age. But around these years, and this is quite common in the Arctic, you have warmer years. Now, what is very interesting, it is when you compare the Varves thickness record exactly taken from the same core, and you see this is normalized Varves thickness, and you see that we have a story that is completely different. And why this is the story that is completely different is because we have rain events, and the rain events are adding some sediment thickness to the Varves thickness. So basically, it is by combining different kind of proxy on the Varves that you can have a better and more complete idea of the climate. Another place I want to walk you through is Saltwood Lake. This is the lake probably around 1st of July. And these are the sediment the clastic Varves that I already showed you. So I'm not going back. I just wanted to show you a nice picture of the Arctic. And here on the left side, you have the sediment core with on top of it the titanium profile. And I told you the titanium is usually indicative for datutic elements. And basically, when we do very precise analysis of these peak in titanium with an image analysis and scanning electron microscope technique, we can measure the grain size, and it's always these peak of titanium are really linked to the amount of medium silt. They are indicative mainly of medium silt. And the medium silt are associated with snow melt intensity. That's also something I mentioned earlier. Now again, we have a correlation between this micro XRF signal that we measure. Here we have a correlation with the weather station that is here called Eureka. So Saltwood Lake is here. It's only 80 kilometers away, and we have a longer instrumental record. So it's a more favorable position here. So what we have here is the titanium measured in the Varves of the lake. And it is compared with the number of days with snow on the ground after June 1st. And you see we have, again, a nice correlation. And you see that we have here, to the opposite to Cape Bounty, we have a decrease in the amount of snow, except for this year here. That's the instrumental record at Eureka. Now, what we want to do, of course, we don't want to it's not really useful to reconstruct the climate of Northern Ellesmere Island, where nobody lives. So what we are looking at is the teleconnections. And here we make the teleconnections with the Atlantic multidecadal variability or Atlantic multidecadal oscillation. That's more or less the same thing. And this AMO or AMV is basically the average of anomalies in sea surface temperature. And as you can see here, these are the typical graphs for correlation for teleconnections, where the red are very high correlation values, and this is for the AMV anomalies, and you can see that Southern Flake is here, is well in the place where we have the strongest correlation with AMV. So we can say that Ellesmere Node and Ellesmere Island is influenced by the Atlantic multidecadal variability. Now, if we go back to these indices, so the AMV, that is the AMV in positive mode, but in negative modes, it means that we have colder North Atlantic Ocean temperature and also lower pressure over the North Atlantic and the Ellesmere Islands. And we can see here that we have a very strong correlation, even better than the instrumental record that was measured at Eureka, with the AMV index and the number of snow on the ground at Eureka. So Eureka and this area is well under the influence of the AMV. Now, if we make the comparison between titanium at Southern Flake and AMV, we have a very strong negative correlation. And if we compare directly our instrumental AMV with the titanium flux measured by the iTrax year by year, year after year, we have a pretty interesting correlation between what we measure and the climate. So this is something that can be extended to a much larger region, of course. So that's what we did here. That's a reconstruction for almost the last 3,000 years of this AMO or AMV, and we can see that we have the current warming period, the Little Ice Age, the medieval anomalies, a warmer period, and so don't remember this is annually resolved. Okay. So we were wondering if we were just, bullshitting, as we say in English, with this reconstruction. So we compare that with very well accepted reconstruction of temperature, and this was here you have the reconstruction made by tree rings, and here under the red curve here is the temperature reconstructed by tree rings through the pages 2K group. And you can see that the two curves are overlapping very well, except at some places. Of course, the correlation is weak, but remember we have almost 3,000 data points, but we have a significant P index that is very, very strong. So let's leave the Arctic and go now to Labrador. Labrador is in the eastern side of Canada, so it's a little bit more south. The map here is barely visible. I'm very sorry, but it's basically you have Quebec, Labrador here. It's really in the eastern part of Canada. This is Grand Lake, and here we have a bathymetric map of Grand Lake. This is a fjord lake that has two major rivers feeding the lake. This is more than 200 meters deep, and we have very beautiful Varves here. It's probably the most beautiful Varves that I ever saw. And you have the thicker Varve closer to the river, and the thinner Varve in the distal position, so almost 50 kilometers away from the source of sediment. Again, here you have the CT scan picture with the HU profile, and then here you have several chemical profiles. You have calcium, you have strontium, and I guess this is iron. Yes. And we can really see very closely and really follow the limits of the Varve. Here you have the same thing, but on a thin section. That's a blow up of one of these parts over there. And we can measure these profiles years after years, and what is interesting is that in this setting we have an instrumental record of the river discharge, and here on the right panels here are different hydrograms, measured hydrograms, and you can see that, for instance, 1983 has a lot of water, and the 1983 Varve is very thick. So the model the theoretical model is working. To the opposite, if you go to 1995, it is this Varve here. It's a very thin one, and you see that there are a lot less water that enter into the system. And again, we can do correlation with Varve thickness and the total discharge, and we have very good correspondence between the two records. So in blue, that's the measured, and the Varve thickness, it's a black one. And we've been able to do hydrological reconstruction with that. But if we try to use the XRF data, in this case, we haven't found any correlation. So it doesn't work all the time. First cautionary note. Now here is a little bit, I'm sorry, this is quite small here for the room. Usually it's projecting on large screen. Sorry for this. So this is the results from a lake in Poland. You have the micro XRF data that are the upper panel, the upper curve here, and then you also have the profile measured by the hyperspectral scanners, where here you have the bacteriophile fitting and here the total chlorophyll. And you see here we have Varves that are very thick. You have all the boundaries of each Varve, if it is 2011, 2012, 2013, and so on. And look at the total chlorophyll here. We can really see when the diatom blooms or the chlorophyll is produced in the lake during the season. So it's really seasonal measurements that these people have been capable of doing. And on top of that, they tried for the same set of years. They have a long-term monitoring program on the lake itself, where they have record the temperature, the atmospheric temperature, but they also have measured the temperature of the water, but also the presence of mixing. And you have here the oxygen content at the bottom of the lake, and you see that you have episodes of anoxia. And you have to believe me, this is basically found as well in the sedimentary profile and the measurements made by the hyperspectral scanner with the indicator of the bacteriophile fitting. So this bacteria that is indicative of an anoxic boundary in the lake. And of course, with that kind of calibration, you can of course start to make a reconstruction for the whole Holocene. I won't go, because this is a record for the whole Holocene, but I won't go into the detail of this paleoclimatic reconstruction. I invite you to read this very good paper in Science of the Total Environment. But you can really see that there are different episodes. That this one, for instance, is a period where the human impact has been quite important. Due to eutrophication, you have more bacteriophile fitting, and so this is an indicator of a human disturbance. So I will finish with some concluding remarks. So scanners can provide annually resolved data in various settings. The correlation between scanners data, whatever scanner that you use, is complex and has to be done for each site that you are studying. The correlation with climate is not always present, as I showed for Grand Lake. Another thing is that you need to have Varves that are thick enough to be able to recognize them. So, and basically, if your scanner doesn't have the resolution to provide at least 10 measurements per Varve, you will not be able to define the Varve, because you will have too few data sets. Another thing is the alignment between these high-resolution data sets is very tedious because, first of all, the size of the pixel or the voxel size are different from one instrument to the other one. You are not measuring exactly, never measuring exactly at the same place. And one cautionary note is that the Varves and other annually laminated proxy are not always straight or horizontal in this case. And this is an interesting exercise that Mike Marshall has done in quaternary geochronology. Basically, he did artificial Varves, and he was basically making this Varve tilting by 1, 2, 3, 4, 5%. And here you basically make a profile of the gray level value over a width of 4 millimeters. That is the upper row, and then over a width of the 8 millimeters. This is the lower row, and you can see that depending the width of the profile that you do, you have not the same result. First of all, if you make a profile on a larger area, your wiggles are disappearing, but even worse is that at the end they are in antiphase with what is the reality. The second thing is that to the contrary of speleothems, the sediments it can be moving even if you store them in very pristine conditions. Here's an example of a medical CT scanner of two sediment cores, one taken in 2005. The other one taken in 2006. They look very similar, but if you do the measurements, so the red curve is 2006, the blue curve is 2005, you can see, okay, there is a good agreement, but then it starts to go again in antiphase. So, and this is basically due because we haven't been doing a good job in 2006. The sediment has desiccated a little bit. And so here the alignment is not valid anymore. So this is also a big difficulty for using this very high resolution scanners on these bars is really sometimes something complicated, and they allow of variables that makes the work difficult. And with that, I will thank all these people that have been contributing to many of these examples that I showed, and I will take any question with pleasure.
Thank you so much, Professor Pierre Francus. And if you want to make, se vocês quiserem fazer questão de português também, posso ajudar a traduzir. Or you can make questions in English directly to him.
About this tilting on the sediments, it's possible to correct if we have the image of the original one.
Yes, it's possible to correct, and there are actually some software that exists where we can basically take one picture, then the other picture, and then realign the two signals. But this is very, very tedious. You can ask Margarita. She has been trying. She has been trying because the desiccation, for instance, for the example I showed here, the desiccation is not regular. It's more intense in some places and less intense in other places. So you really need to follow that very closely. For the Lake Iowa core, I spent also a lot of time simply. It was the same core, but they were transported by FedEx and so on. And so some of the cores were had moved in during the transportation, and we had to do this exercise as well to be able to correlate the XRF profile with the discrete samples that have been taken in the core and the discrete analysis that have been taken in the core. It's less problematic probably with the speleothem. Hopefully it's not shrinking or something, but
Professor, quais os parâmetros que eles escolhem para dar zoom maior, detalhe maior?
She's asking what is kind of the parameters you could use to zoom out and in.
In the MicroCT scanner?
Yes, why did you zoom in that part? And what is there?
So so if I understand correctly your question, if I go back to that slide, let's see this one. This one, right?
Yes.
So here there's a full sediment core that is 1 meter long, okay? If you were analyzing with the full resolution, you will have files that will be gigantic and it will take forever to make the analysis.
Yes.
And this is not practical. So basically, with the MicroCT scanner, we do exactly the same way that we would do with a thin section. We open the core and we make a subsample of the core to make some sort of composite sequence of smaller region of interest that we are more capable of handling in terms of time of acquisition and size of the files. So basically, you look at the best place where there are less disturbances. I would say, if in the case of a speleothem, then you will choose the places where you will follow basically the growing path of the speleothem to follow the best paleoclimatic section. And with that, you can avoid the disturbances that are sometimes often on the side or these kind of things.
Thanks.
Any more questions or questões? Okay, I just want to have your opinion about the potential to use those techniques in other samples, for example, carbonates from speleothems or from other kind of deposits, not only lake, but other deposits. Could you please think about your opinion to use, because you have interacted in the last days and you saw many samples of speleothems, and probably you are thinking about how to use them, if it's possible, and how would it be to use the same techniques?
I mean, the MicroCT and the CT scanner can be used on very, very, very different objects. We've been studying soils, we've been studying frozen soil, permafrost, we have been studying ice, the structure in the ice. So you can basically put the ice core to measure the size of the pores. We never tried the MicroCT or the medical CT on a stalagmite or a speleothem. But I know that people studying corals do.
So why not?
So why not try to do that for the
How
speleothem?
thick could be the slab that could be used to this kind of technique?
So that's for the MicroCT. Basically, the best object for this MicroCT and the CT. This is a cylinder. Okay, so a slab. Yes, it's okay, but there will be artifacts, and the artifacts will be not for the measurements, but from the 3D image reconstruction, so the mathematical reconstruction.
That make a cylinder out of
Yeah.
speleothem.
So, a round speleothem it's a good geometry to do an analysis. For the micro XRF scanner and for the hyperspectral scanner, I don't know too much about the hyperspectral scanner, but for the MicroCT scanner, there might be some problem with X-ray diffraction. So here we have X-ray that are bombarding the sample, and then photons are detected. But if you have single crystal of calcite with a, how you call that in English? a plane of the crystal that is just in the right direction and shoot back, diffract back an X-ray into the detector, then you will have artifacts.
Okay.
And then you will have false peak in the EDS spectrum.
We've got to find samples that are well laminated and not so large crystals
Yes, you probably should
The
avoid
contrast.
large crystals, yes.
to give the contrast between one layer to the other.
That's right.
Okay, good.
High-speed spectral scanner probably will detect the organic matter somehow, which I don't know if I haven't seen anything about hyperspectral scanner on speleothems.
So it's some valuing to use these techniques also
Mhm.
for other samples like speleothem.
Yes, the beauty of these techniques is also that you have an archive, you have a visual archive of your sample. And basically, if you don't have enough room in your storage, you can still have the digital image of your sample with the medical and the MicroCT scanner.
Okay, really nice. Okay, so if anybody has no questions, tem mais questões, então, I'd like to say thank you so much for your nice presentation. It's so valuable introduction of several techniques that could be used here in sediments and lake sediments and also in other kind of archives. And yes,
We want to thank you too for participating of the group.
Yeah,
Yes, and thank you for you two to be contact and everything.
okay, so
okay,
I want to say something for the page.
okay.
But thank you so
Sure.
much. I don't know. Tô aparecendo? Eu só queria agradecer todo mundo que participou aqui esse ano com a gente no Café Geológico, que curtiu a página, seguiu. Nós estamos quase chegando a 2.000 inscritos, então se inscrevam, que em 2.000 a gente consegue ganhar alguma coisa, comprar café para ter café no Café Geológico. Então é isso, essa é a última palestra do ano. Obrigada por quem participou. E ano que vem estamos aí novamente, tentando trazer sempre esse híbrido, sempre que pudermos. E é isso, obrigada.
okay.